So the parametric spectral analysis, okay, we already discussed what is that. So the parametric spectral analysis is because the power spectral density, which is estimated, depends on the set of parameters. What are these parameters? Now, in parametric spectral analysis, it is the power spectral density is organized, so is obtained by a ratio of polynomials in Z transform. Which means, I have a ratio of polynomial with a set of 0, with a ratio of polynomial with a set of poles, and the zeros and poles depends on are the unknown parameters. So it depends on the polynomial coefficient A and polynomial coefficient B. Polynomial denominator is monic. Monic means the first coefficient is 1. Okay? So the unknown for spectral analysis, here are the unknown, are the set of coefficient B, the set of coefficient A, and these are sigma. Okay? These are the set of parameters. So, the total number of parameters, okay, is 2 times NA plus NB, which is the number of parameters A and the number of coefficient A and the number of coefficient B, plus 1. Why is it 2? Why is it 2 times the number of coefficient B and the number of coefficient A? Why 2? It's the number of coefficient B and the number of coefficient A. So it's the size of B and the size of A. Why 2? Square, not square. Why 2? They are complex. These coefficients are complex in general. Okay? If real, then it is NA plus NB. But in general, there are 2 times NA and 2 times NB, because I have a set of complex coefficients. Okay? If I don't know what is the power spectral density, then what I can say is that these are complex in the general case. Okay? So these 2 for generality, that a complex value. Okay, so it's a real part and imaginary part. Okay, so that means that the number, the theta is my parameter. So what I need to estimate is this theta, which is a coefficient of polynomial, which gives me the 0, the coefficient of polynomial, which is giving me the pole, and then the scaling factor, which is sigma. Okay, sigma is acting as a scaling factor, so it's making the power spectral density bigger or smaller. Okay, now how to do that? Now, what I need to do is I need to write the Laplace function. So what I need to do for this case is that I remember that x is Gaussian with a 0 mean and covariance CXX that depends on theta. So I'm using this model that, by the way, we have never used before. Okay? So we're using the model that the random process, the random variable, is a 0 mean with a covariance CXX. Now, this CXX, okay, this CXX is parametric with respect to theta. So if you go back to the formulas, if you remember, we were saying that, we have x is normal with the mu that depends on theta, and with the CXX that depends on theta, okay? And then, this is the most general one. And so what we did in the past, we said that, we might have that the covariance is not dependent on theta, and the mean is dependent on theta. So this is the kind of problem that we have been solving so far, which means in the past, for maximum Laplace. Now the new model is this one, where this does not exist, which is 0, and this one is depending on theta. So this motivates that model. Now, You know, this is the typical model which is used for parametric spectral analysis and line spectral analysis. Line spectral analysis means I have a spectrum which is represented by lines, by delta, which is by sinusoid. Okay? So line spectral analysis is a technical name for having the estimation of the multiple sinusoids in noise. We are not treating that. You go to the book, we are not treating because it's going to take at least a couple of weeks to treat the estimation of line spectrum, which is estimating of sinusoid. But you know, I encourage for those of you that perhaps in life they need to estimate sinusoids. When the sinusoids are multiple, remember that this specific problem is called a line spectral analysis. Okay? So even the name is important to know where to search. So now let's go back. So how can we write that? So you know, if we look at the probability density function, because of where we start for writing the maximum Laplace is we write the Laplace function. So the Laplace function is dependent, okay, on some parameters. So you know, if you remember, let me write that. I sketch it. I don't even stand up, but you know, because you know that. So the probability density function of x in this case, when it is Gaussian, so it contains the determinant of Cxx, and then it is exponential. Okay, it contains the covariance Cxx to the minus 1. Okay, so this is the reason why I'm computing that part. Okay, so the Laplace function now, it depends on the covariance, that depends on theta, and depends on blah 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 with an exponential. We have been always calculating that because this guy was not depending on theta. So the novelty now is that the covariance depends on theta. Now, so that means that here I have the determinant, and here I have the inverse of the covariance. Trouble. So how can I compute that? Now, the way to compute is just this one. So the determinant is equal to the product of the eigenvalues. So, but you know, if every eigenvalue can be approximated by the power spectral density, then I can replace in this approximation, you know, the product, which means the product of all the power spectral density computed with uniformly spacing 2 pi divided by n multiplied by k. Okay? Here, you see the link now? Okay? I mean, if I ask you to write the Laplace from here, you could not write it because you don't know what to write here and what to write there. Now, you know that this is the first, we say, the first useful relationship with which is helping us to write the Laplace function in this case. So this depends, you know, here in this part it goes the product of the power spectral densities here in place of this. Good. Now there is the inverse of the covariance. So then let me write this one. Let me write the complete expression. So I have x transpose Cx that depends on theta x. Okay, this is the Laplace that I need to write. So what I need to write is inverse. Okay. So what is that inverse? I know from the eigenvalue decomposition that the inverse of a matrix, of a square matrix, symmetric square matrix is equal to the 1 over the eigenvalues multiplied by a sum of qk remission, which is a rank 1 matrix. So it's a sum of rank 1 matrices, which makes the inverse. And now, since this is approximated by the power spectral density. Since QK is approximated by VK, then, you know, I know perfect, I know everything. So, writing now there, let me write now here. So, what goes here is this. So, in place of that one, in place of this term, I have a sum. Copy, on K from 0 to n minus 1. Of what? Of the eigenvalues, then it's the power spectral density, which is 1 over S 2 pi divided by m multiplied by k. And then it is Vk emission. Now, it is pre-multiplied and post-multiplied for that. Okay? So, but you know, X transpose goes into Vk, and Xk emission goes into X. So, what is this? It is Vk is the basis of the DFT, you see there, multiplied by the data. What is this? Is the sinusoid, is the product between the basis of the sinusoid, kth sinusoid, multiplied by the data. This is the data, a sample, piece of data. What is this? No idea. Huh? Projection, fine. It's a projection of the data onto the kth sinusoid. What is this?
Coefficients of DFT.
Is the DFT computed at the frequency k of x. Okay. What is the other? So xk multiplied by vk. So, you know, grouping them, this with that is the DFT k of x complex conjugate. So DFT-X complex conjugate. So this is equivalent to write the sum of 1 over S 2 pi divided by m multiplied by k multiplied by the DFT k of x to the square. So if I divide by n multiplied by n, what is this? Is the parallelogram. Okay? So this one is the parallelogram. So you see the parallelogram, I mean, we push the parallelogram out of the window or out of the door, and it's coming back into from the window. See? Now, once you put all the pieces together, it comes out that, you know, the log latitude, so if I do here and there, it comes out that the log latitude, okay, can be written in a closer form as dependent on the parallelogram calculated for on frequency divided by the true power spectral density, depending on the parameter theta. Now what I did, you know, I took n very large. So if n very large, the sum reduces to the integral, okay? So now this is the second step. So I'm considering number of samples so big, then, you know, the sum has been replaced by the integral. And this is the reason for that. So if I want to calculate the maximum latitude estimation of the 4 parametric spectral analysis, I need to compute that. And so we got this one. You know, similarly, I can compute the Kramer-Hall bound. I can compute the Kramer-Hall bound for a parametric spectral analysis, which goes from the Fisher information matrix. Luckily, you know, we have a formula which is describing the term, which can be derived. It's a Whittle formula. So the Whittle formula is giving me the entries of official information methods. So, you know, so we have a perfect structure that is, that we will specify, we will specialize to the case of autoregressive spectral analysis and moving average spectral analysis. So, but you know, the formulas which is related to autoregressive and moving average are easy, but they're coming from here. If you don't write all these infrastructure, you never calculate the Kramer-Rao bound. Okay? Now, you might question if the Kramer-Rao bound is useful in this setting or not. My answer is useless for 95% of the time. Okay? But you know, there are that 5% is better to keep in mind in case you need it. So let's go to, let's specialize. Now, how is carried out the autoregressive spectral analysis? Now, the autoregressive spectral analysis is assuming that the specific observation, limited observation X, has been modeled by a white random process W. It's not noise, it's a white random process, okay, W, which is filtered by a filter represented by all poles. And Xn is the output. So now you know, that means that if I know A, or actually if I estimate A, and I estimate sigma, I get the power spectral test. This is what I have. And this is what we will do in 15 minutes, okay, with the data that we have. Now, how to solve that? Now, the maximum likelihood method gives, after manipulating the formula, gives a set of n+1 equation, which is the Euler-Walker equation. Nice. So, you know, and the Euler-Walker equation now is carried out with a limited set of data because you only have n samples. So, how do you get your n samples? Our n samples are obtained by the biased estimate of the autocorrelation, which is indicated as R hat. So, once again, I have the Euler-Walker, fine, which you are familiar, and now you understand why, you know, I mean, the autoregressive spectral analysis is an application of the Euler-Walker equation, okay, by using the bias sample autocorrelation, okay, which is, just to remind you, is the one where you have 1 over n sum of x and x over n x and x n plus k. Okay. So this is, you know, the sample autocorrelation, which is the one that you get by fixed coordinate. And you have the flag, which is bias. Okay, so you use the bias. So you calculate in this way. You take the first samples. Actually, you take, you know, the first NA plus 1 sample of the autocorrelation, and you plug it to the Euler-Walker. You solve it, and you get A. So that means that here, what we do is from Rf x to the coefficient A. Okay. We use the Euler-Walker in this way. Finish. Autoregressive spectral analysis is simply using the Euler-Walker. Now, in the exercise, I cannot ask you to calculate the sample autocorrelation, so I give you the autocorrelation. Okay? Or you derive your own autocorrelation. When I ask you to calculate the autoregressive spectral analysis, I'm asking you to calculate the filter which generates a specific process that you fit. So you fit an autoregressive model with an order that perhaps I give you, or usually I give you every exercise, onto the data where you know the autocorrelation, which means I given the autocorrelation, you know the coefficient. Okay? Now this usage of the this usage of the Euler-Walker equation is the same as if, now I changed the color so it's another subject. It's similar as if I calculate the prediction filter of order A such that the output is epsilon n order n. So I can calculate the linear prediction filter of order n. So making the autoregressive spectral analysis is equivalent to take a set of samples and compute the linear prediction filter, which is optimum in a sense that is minimized the mean square error. Now, since it's numeric, the way, since it's is on a limited set of samples, the way you compute the linear prediction is not unique. And so the way you can compute the linear prediction might be slightly different from the one we discussed, which is going through the Euler-Walker. If you go to the book, there is, now I go by memory, but I remember I wrote it, and there is a section where I write a least square linear prediction. So that is another strategy that you can implement to calculate the optimum linear prediction and linear predictor. In this case, if you calculate the linear predictor, which is optimum, you are implicitly computing the autoregressive spectral analysis. So, linear prediction and spectral analysis, they go one by one. Okay? Now, for the Kramer-Rao bound, if you need to compute it, in case you need, the Kramer-Rao bound, which is the covariance of the set of coefficient, and the coefficient are the set of coefficient A and sigma, autoregressive. Okay? This is equal to the inverse of the covariance for the coefficient A, and it depends on the square. The covariance depends on the square of the power itself, which means 2 times. But it means that in this case, the covariance depends on, should be the 4th power. It's here. Okay. It depends on sigma 4. It depends on the 4th power as well. Okay? That's this confirms that in spectral analysis the dependency on the variance or covariance, like in this case, is always dependent on the 4th power of the excitation. Furthermore, the coefficients A and the power are decoupled. It makes sense because the power is amplifying, so moving the power spectral density, making it bigger, smaller. And A is ruling the poles. And the poles are where the power spectral density is. So, if you scale sigma, you can make the power spectral density bigger. Okay? And scaling the pole is defining where are these say, resonance. We will see the resonance as well. I'm going to show it as well. Second, moving average. Okay? You see, there is nothing else. I am keeping short of the story of autoregressive because we started to talk about autoregressive since the beginning. And this is, favoring us to have the autoregressive random process almost floating, almost, being naturally into our reasoning. Now, moving average. You know, the moving average is more simple than you can imagine. So, the moving average is carried out by assuming that I have an excitational random process, y, with the power sigma square, ma square, depending on the order, filtered by a filter with all zero. Okay? Now, that means that, you know, the power spectral density, you know, the parameter are the set of coefficients and the power. These are the unknown. And the power spectral density is simply given by the polynomial, where in place of omega you put in place of z you put aj omega. Nothing new so far. Okay, so which is described here. Now, because of the property of a power spectral density, we know that the power spectral density is obtained by the z transform from the polynomial times the polynomial flip and with complex conjugate. This comes from the theory. So far, here it is. So now, how do I get the coefficient? I get the coefficient by the sample estimate of the autocorrelation, biased one, the biased estimate. So what I do, I have a set of sequence. I calculate the autocorrelation, the biased one, and you know, and then computing the z transform of this autocorrelation, I get this polynomial. It's always finished. Okay? Now, but you know, it cannot be so simple. And now let me tell you why it's not simple. We will make quite some exercise on that soon after the Sunday, so which is next week. Okay? But I mean, let me tell you what is the key aspect. Let me tell you conceptually, and then you know we discuss practical implication. Now, if you calculate the biased autocorrelation, this. So if you calculate this one here, you know, and you know that the process is moving average. Assume that I know that the process is moving average with order 3. Okay? Now, what does the theory say? The theory says that, you know, after 1, 2, 3, so after 3, and similar here, so after 3 here, in theory, all the coefficients of the autocorrelation should be 0. This is what we know. Because, I mean, if it is a moving average order 3, it has been obtained by taking a sequence with 3 samples and convolve with itself. Okay? So, you know, it's 0 out of there. But, I mean, if I make it with a sample estimate, then it comes this way. It's not 0. In sample number 4, it's not 0. It's not 0 because, I mean, it's due to the fact that I have a limited set of samples. In sample number 6, it's not 0. In sample number 7, it's not 0. Sample number 8 is not 0. It's fluctuating. Perhaps, you know, is the shape, you can understand the shape, but it's fluctuating. Keeps fluctuating. Now, this fluctuation is due to the fact that, you know, n is minus infinite, which means n is limited. Okay? So if n is going to infinite, ideally, then, you know, perhaps we'll get a nice autocorrelation. And this gap is going to 0 after that. But I don't have an infinite number of samples. So, what to do? I don't have an infinite number of samples. I have a finite one. But you know, my sample estimate is fluctuating. By the way, it's also there. And it's fluctuating. And the true one is there. So, I mean, what I can do, I can take the first 3 I take this and that, right? So I take the sample from -3 to 3. By the way, they are symmetric, so from 0 to 3. Because the autocorrelation for real signal is symmetric. Huh? So I take from 0 to 3, as it is. Why is a bad choice? Because I'm truncating. So if I'm truncating, that means that on that autocorrelation, what I'm doing is R hat n is multiplied by a window n. And this window is rectangular. Right? Which is a 7. So okay, so it's n. Okay, so it's a rectangular. So since that one is rectangular, you know, when I make the Fourier transform, and I make a Fourier transform of this rectangular, what is the Fourier transform? It's a sink. And the sink is positive and negative. And so what happens is that, you know, I'm estimating a power spectral density that does not have the property of having the zeros in the position complex conjugate and the reciprocal with respect to the one another. So here it says they should be reciprocal, okay, with respect to the unit circle. This is what it says. You know, what I find is not a set of zeros that are reciprocal. If they are not reciprocal, this is not the power spectral density. You know, perhaps in some cases you can find that when you estimate the sigma that is a negative. Okay? Worse than worse. So, how to do that? So you apply a triangular window. So what you do here is that you don't take this, but you take this one, multiply by triangular window. Because rather than truncating, you are applying in place of this a triangular window. Because you are, after multiplication, you are convolving with this Fourier transform. And the Fourier transform of a triangle is positive definite. Okay? So, this is the only care you need to put. The only care is that every time that your own data, you need to pre-window to limit the length of the sample estimate by a triangular one. So it's, you know, the autocorrelation that you estimate is biased by the effect of 1 over n, and the further biased by the effect of the truncation. And this is this rubric. Recommended the window that has a positive definite Fourier transform. Okay? Or positive, semi-definite. Okay? Now, this windowing is mandatory. This is mandatory. Okay? Now, so, you know, and this one is, this comment is saying that we have a set of roots that are in a reciprocal position with respect to unit circle. Now, we make exercise on that, such that, you know, I mean, I'm not doing much exercise on applying the Euler-Walker, because we have been applying, you have been applying, I mean, in every flavor, and I perhaps make a linear prediction, but rather we make a couple, 2, 3 exercise on moving average spectral analysis, or a mixture of that. Now, let me show you what I did. Let me show this practical case. Oh, it's turning off. Okay, so I promised you to show you a little bit, and then you know this is what I prepared. Now, rather than writing the code on the fly, okay, I use my lunch time to write it. Okay, so it took 1 hour approximately because I tested. I wanted to test it. Okay, so for this reason, you know, anyway. So let me see. Let me show you how this code is structured. So I have one data set which is coming from a vibration system, okay, and it's data vibration. I don't know if we need data vibration for. Now the data are structured into a table, and I convert it into a set of data. Now you know the data so are organized in columns. In the first column there is a time. In the second column there is noise. But the noise, why is there is noise? The noise that you measure, or the noise that you...
Because the noise affected the data, the transmitting line. So we have to consider that.
But did you cancel the noise?
No, it's not that we know how much is the noise.
Ah, okay, you did not cancel.
No.
Okay. So, you know, let me show you how is the structure of the code. So I give you the code after, of course. Okay. So I structure in this way. The code is structured in this way. So there are two files. One is the real data, and the other is the simulated. The simulated that I have, which is this NT, so I generated NT samples. NT is 10 to the power 6. I can change it. This is the time. I put omega, and then I have a sigma W, which is the noise, and then this is the signal. So I generate a sinusoid. So the simulated is the sinusoid. It's the cosine omega 0 m plus the random phase, okay? Plus Wm. So this is characterized by a sigma or sigma square, and this is parametric with respect to omega. Okay? So I call the time, I indicate the time with the vector t in order to collect all the samples, the generation of the samples. Then for the periodogram, okay, I used this is the block of periodogram. So I have periodogram, and the periodogram, you know, is parametric. I have a set of some parameters, and I have the output of the power spectral density represented. Okay. Then I have autoregressive spectral analysis, and then as the output I have power spectral density. Okay, estimated by the plot estimated by the autoregressive spectral analysis. Okay. Now what I also did, since the autoregressive is estimating the model, so the model is 1 over A, which is Z, and then is a set of coefficient A here. And then, you know what I did? I calculated the roots of A. So I wanted to see where are the poles of the autoregressive spectral analysis. So my goal is to see where are the poles. Okay. This is the structure. So, and you know, I also have the plot, which is a z-plane, I guess. Z-plane is plotting the position of the pole. Okay, this is what I did. So let's work a little bit together. So let's load the data. So I start loading the data. Then I prefer to look this way. Okay, it's docked. Check it. Now, so let me see. I loaded the data. Let me see the workspace. Oh no, let me clear it all. I tested before. Okay, I check if the if the data are there. I use the channel number 3. Okay. By the way, these data are organized in 5 columns. Here is the time. Second column there is the noise. That has not been removed, which is a nice exercise to remove, right? Okay. And then there are 3 columns. So what
It's what is it?
X, Y, Z. Okay. So it's the 3 axes of the accelerometer. Okay. These are 3 axes. So now I choose one. Okay. These are the poles, but don't look at the pole. We will see later after. Okay. Now, so I choose the channel number 3, which is X, the first one. Okay. So now let's do the parallelogram. Now the number of samples, or before proceeding, what I look at is the number of samples. So it is 205. So it's 2 to the power of 5. Okay, approximately. So the length of the 5 is 2 and 10 to the power of 5. Okay. So I mean, since I have so much data, I have a wide possibility to segment the data. Now, if I plot the data, oh, X is already there. Okay, this is the data, so means nothing. Okay, perhaps we can zoom in because there are too many samples. Okay, now zooming a little bit, you see it contains some sinusoids. It contains an amplitude modulated sinusoid, at least, something like that. Okay, look at the data, always. Look at the data. They are not untouchable. You're better to look at what you're doing. Okay? Because, don't get surprised. You should never get surprised by the process. The process should confirm what you see. So now, what I did, let's start with the parallelogram. So what I choose is a parallelogram with 1024 samples. I use a Welch. Welch is the method with the windows, okay? Now, I choose, let's start with the boxcar window. Okay, the boxcar is a rectangular window. So I decided the window is rectangular. That's because the Welch, let me see. Okay, no. Where is the L? Here. So when I look at Welch, so PXX is P Welch of X, which is, I can just use the data and then, get the power spectral density. What I did is to use the Welch with the overlap and the size of the FFT. So the power spectral density PXX is the P Welch of X is the data. Window is the shape of the window, which is the coefficient of the window. Overlap is the degree of overlapping, we will see in the data, and then FFT is the size. So going down, window uses the input vector or integer, window to divide the length, the signal into segments. If the window is a vector, P Welch divides the signal into segments equal to the length of the window. So essentially, segmenting. No, the overlap. Uses the overlap, number of overlap samples, or overlap from segment to segment. Overlap must be positive integer, smaller than the window, smaller because it's the overlapping part. Okay. Where is it? Here, overlap. Positive integer less than the length of window if the window is a vector, as it is for us. If you don't specify overlap or specify overlap as empty, the default number overlap the sample is a 50% of a window length. Okay? So that means if I put here the overlap as empty, and then is overlapping by 50%. Right? And FFT is the size of the FFT that I'm using. So 1024. And now figure, so I put in figure 1 the power spectral density, and then I put omega, and then it is 10 power log 10 of the x-axis, so it is in decibels. Okay, so the power spectral density is in decibels. But I also prepared the power spectral density in linear scale in case. Okay. So now let's run this. And then this is the power spectral density by the parallelogram. Okay. So what we notice is that there are a set of lines. You have a strong sinusoid, a strong resonance here. We don't know the data, so you know the data. Okay. So there is this resonance there, and then there are other resonances, in a lower frequency. Probably, that's what I say. Okay, probably, these big resonance, these results, since I have several harmonic, might be a result of other excitation on the lower frequency, which is making the resonance to resonate the structure or whatever to the higher frequency.
Actually, they are chatters.
They are?
Chatters.
What are chatters?
If your profile, because the data are not grinding machine, when a rotating wheel, that the piece is rotating. If the profile of the piece has a shape and every dot revolution, they found the mesh on the grinding wheel. It causes chatters and it causes resonance.
So it's rotating. Okay. You see, we need to know what is the application, So we have a perfect, you have a perfect example of how it's working. So he has the problem, he gives me the data, and then in order to understand, we need to understand each other. I don't enter into the application. Okay? This is what I've been doing in 25 years already. I don't enter into his application. He's giving me the data. This is what, I'm trying to transmit to you. You don't enter into the data, but you have your tools. Okay? So this is what I see. Then, I talk with the application. Then perhaps he says, I want to see, what are the period here? I want to see, because this might be some nonlinear effect. Or, I don't know. Because if you hit it, so probably it's hitting is not sinusoid, and then it creates harmonic. Okay, so if I do this way, it's this hitting or making even more abrupt. Okay, this hitting is not a nice sinusoid, so I cannot generate a sinusoid. Okay, so nice to know. Now,
Professor,
what?
Sorry, I have a question. If we have 1024 samples and we define with the boxcar a rectangular window with the same size, shouldn't we choose a smaller window that goes?
The boxcar is not applying the window, actually.
No, but we define the filter, right, with the boxcar?
Yeah. With the boxcar is non-filter, is non-window.
Okay.
Since I don't know how to force the Welsh algorithm to operate with a rectangular one. So I want to be sure that I do it with the rectangular. Otherwise, what I can use the parallelogram. So there is this code, and you see the syntax is very similar. So I have a X, a window, and FFT. So let's use this one, parallelogram. which is similar.
But here for the the
Wedge.
window is given by the boxcar.
Yeah, it's given by the
That
box.
has the size of the data. So the window is always the same size?
Yeah.
as the data? Always?
Yeah. No, this is the segmentation. So I'm tick, 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 window with a rectangle.
Okay, but
I mean, what I'm doing is this. No, let's see. What I'm doing is this. I have all the data which is very long. So I'm taking a rectangle one, a rectangle one, a rectangle one. By the way, it's overlapped by 50%, so I'm making rectangle, rectangle, rectangle. And then this is computing the average of simple parallelograms. This is what happened in this case. So if I look at this one in linear scale, let's see. I put it here, but it's for another scope. Recopy. I see only just the peak, okay? I don't see the other resonances. This is the power spectral density in linear scale. I can just see this big spike, big sinusoid. So I can notice there is one sinusoid, another, probably another one. I don't see them. So I better to look at in logarithmic scale to see all the others, because the dynamic is too limited. Now, if you have a plot like this and you start with linear scale and then you see there is a second peak then another, you need to expand the dynamic. And so the way to expand the dynamic is by plotting in logarithmic scale. Okay, now, if you want, we can, if you don't want, if you are against the dB, what you can do is that, you have here, the y-axis, and the scale is okay. So we plot in log scale. So flipping linear log, which is very typical in order to understand what's happening. Okay, that's the same data. It's just a way to represent. Now, if I choose, for instance, if I choose a number of F15, which might be 32 times bigger. So I take very, very big window. So what to do I expect? Let me plot in log now, okay. Which I prefer. See? So this is what's happened. So this is what I see, then I'm choosing to use a bigger window, which means because I choose a bigger sub window, the number of sub window is smaller, and then I have a bigger variance. So this fluctuation here, this one, which is outside, is due to the variance. Probably I can see linear scale, probably. Log is more than evident, but I'm seeing linear scale. No. You see, I start seeing these resonances that are not present. Okay? And this is due to the linear scale.
So but the bigger fluctuations is not even due to the fact that the main lobe is more straight because we are increasing the
yeah, but in this case, for this data, okay, I prefer to think that these fluctuations are mostly due to the variance. So I can play with a number of windows. So this is what we have been doing is a clear case where we are trading. We don't know the answer because we don't know what is the true power spectral density, and we are trying to find the true power spectral density for the vibration data from iterating different length of the window. So I prefer not to consider these fluctuations as a true data, but rather the effect of the variance of the predicament. So going back to the log scale, which I prefer. Okay, this is the behavior. Now perhaps if I zoom it, it's too noisy, too affected by the presence of an excessive number of samples. Okay. Now let's keep this one. Okay. So let's hold the plot. Let's remove how to move this. Yeah. Okay. Now I keep the power spectral density and then I use the autoregressive. Now for autoregressive I use the P Euler-Walker, okay, which is the power spectral density calculated for autoregressive using the Euler-Walker method, which is solved in Euler-Walker. So I have the input and AR, which is the size of the autoregressive, so this is the order of the autoregressive. 512, which is the number of samples that I use to compute this sample autocorrelation, because I need the sample autocorrelation. And then the algorithm average several computation of the autocorrelation. And 2 pi is the frequency axis, so it's just a technical. So if I calculate with the 4 poles, I put in the red, okay, so just to make it different. So with 4 poles, okay, now this is the red. I don't know if you see, so I can just translate the red, okay, which is the autoregressive spectral analysis. I translate upward by 20 dB so that we see, okay, or 10 dB, so I make it 10 plus. Okay, so what's happened there? It happens that there is a strong resonance here, and so the autoregressive spectral analysis is putting a pole to that resonance, because that resonance is the most important one. And by the way, it's also quite well describing the behavior, okay, of the power spectral density. Remember, the power spectral density by autoregressive has to fit the overall power spectral density, okay? So as you see, this pole is put halfway between several going up and down of the periodogram estimation. Now, if I look at the pole, okay, that's where the poles are. So I have a pole, our autoregressive of order 4. So I have 2 poles that are placed close to the unit circle, which is giving me the resonance frequency. And there are 2 other poles that are placed here to give me, to set the behavior, which is going smoothly to, not to 0, but to the lower value for lower frequency. So the signal is a high pass, by the way, so it was clear, okay? Now, so, I'm not happy with these results. So, I'm not happy of representing the power spectral density in this way. So, rather than, let me go back to, I take it back, so, I off, and then I repeat with 1024, okay? And then I redraw in this case, okay, with with approximately 1,000 samples. And then I hold the plot and I rerun, the autoregressive just with a very clean signal. It's shifted upward just for visibility, nothing else. So, now what do I technically do? Since every pole is a resonance, so I have one resonance, two resonance, three resonance, approximately 4, 5, 6, 7, 8, might be a resonance 9, 10, 11, 12. So I should use autoregressive of 12 water at least, because I'm counting the resonance. And then I need to put one pole for each, approximately. So, but since I have many others, so probably there are more. So I start with 12. Okay? So this is what I start with. So I start with 12 and then I see, how is it? Okay, so this is, by the way, is shifted upward. Okay? So, if now I shift downward, so now it's quite well visible. I take this one and I replot again by shifting downward. Okay, you see? Look at that. Now, one pole is going there, then there are too many fluctuations. The autoregressive doesn't know which one is more important. Okay? So probably I need to increase the order. This is what it's suggesting. I need to increase the order of the autoregressive. So, we go to 24. And then we run. Now, this is the new plot. So perhaps I change the size in order to understand it a little bit. Perhaps I change the color. Okay. Now, I have one pole here, one pole there, I have a settle pole which goes behind this resonance. There are too many peaks here to follow, but I capture this pole, I capture this resonance, I capture this pair of resonances, and also that one. So I want to see what are the poles there. Where are the poles? Okay, so you see where are the poles now? So the poles are, are trying to interpret at best all the resonance that I get. Now, this pole is very close to the unicircle because it's justifying this pole, this bigger resonance. Okay? And then, there are all the others. Now, since there are these 3 poles that they don't know where to go, so perhaps I reduce a little bit the 24. Because so I start, start removing. By the way, the plot says that there are 24 zeros in the center, which is not touching anything. Okay? So then, I reduce it a bit. So I go to 20. And by 20, I expect this. Right now I don't understand anything. Okay, I remove this. I need to put the +10. I rerun. Okay. So actually, looking at the blue, looking at the red is the new with the 20. I think that we are following quite well all the resonances that I can see in the power spectral density by the kilogram. I would stop. I would probably stop, And looking at the poles, these are the poles. You see, we removed the poles in the center, which were doing nothing. At least nothing for the resonance of the signal, of the process that we have here. So, this is with the signal that we got for him. But, let me do another. So I'm changing the kind of signal. Is it clear? you can do, I give you the code, so you know, can I upload the file of data? Okay. So you know, I mean, I give you the code and the data so you can play, okay? In the same way as I play. Now, I also put a sinusoid, okay? So, you know, I have one sinusoid in noise. So, let me now generate the data, let me clean off. So, I generate the data. Now, this data is a sinusoid in noise, okay? So, let me make it a periodogram. I need to cancel the data. Okay, let me run the periodogram. So, you know, in this periodogram, let me put in linear scale. In here, you know, with the sinusoid, it's better the linear scale. Now, in my linear scale, what I did, I also put the power spectral density of the noise, because we know that the power spectral of the density of the noise is 1. Okay? So the true power spectral density is constant, and then there is one sinusoid. Okay? Now the power spectral density here is 50 to the square. And the power of the sinusoid is 1/4, because you know, okay, the power, the amplitude is 1, so it is 1 to the square divided by 2, and then it, you know, it's 1/2, so it goes half here and half there, so it's 1/4, 1/4. So I'm 1/4 versus 50 to the square, okay? So let me plot now in linear scale. Here, I don't see anything. You see, the red line is where is the power spectral density. Why is it fluctuating? Because of the variance. Okay? So is it fluctuating because of the variance? So I can, you know, I can change the window. No, you know why? And I can change, and I can change the overlap. Okay. My overlap. We need to close it, guys. So now, let me show you something. I want to see the sinusoid. So I know from the theory that the periodogram for a sinusoid is this one multiplied by n. And so because of that, if I choose n large enough, I can see the sinusoid coming out. So if I multiply the periodogram in this way, here, I see the sinusoid coming out. And so, you know, that's a sinusoid, luckily, okay? And then I zoom it, and then I can see, you know, what is the frequency of this sinusoid, okay? This is the aperture. If I make it with the Bartlett, now let me do it with the Bartlett, so, and then I close it, they kill us now, huh? And then I make it you say dash it. Okay, let me rerun. So what I do the Bartlett rather than the rectangular one. Okay. So you see, it's a little bit larger. Now you don't see much here, but you know, I mean, it's a little bit broader. Okay. This broadening effect is due to the fact that about the triangular window. Now, and to conclude one last point, I can also calculate the autoregressive spectral analysis for one sinusoid. What do I expect to come up? I show you. Now, if I calculate the pole, okay, now probably I choose the sigma too big. So if I make a sigma equal 1, I generate a sinusoid, then I calculate the autoregressive spectral analysis for 3 poles, 5 poles. Now what's happening? define function, variable, and is a variable. It doesn't, I don't know. So, and I don't know, guys, we need to go. I give you. So, what I ask you to do for one sinusoid in noise, the autoregressive spectral analysis. You will see that all the poles will find the frequency of a sinusoid, and all the other poles will go to the center. So you can use the autoregressive spectral analysis to estimate the frequency of a sinusoid, because every position of the poles is representing one sinusoid. Okay? Do it by yourself. It's very instructive. And so you can figure out that you can use the autoregressive spectral analysis to estimate the frequency of multiple sinusoids. And my suggestion is do it by autoregressive as far as the sinusoids are far away one another. If the sinusoids are too close one another, you need to use high resolution spectral analysis method for estimating the line spectrum. Okay, which is the topic that we're not covering.